Okay, good morning, everyone. You've made it to the end of the new material for this course. After today, there's just a quiz on Friday and then a review session next Monday. A note about the review session, I have sent out a survey about that, asking you guys to tell me if there's anything that you'd like me to cover. I've only received one response so far. If I don't receive multiple responses, I will take that as a signal that you are fine with the material and you don't want me to go through things. And instead, I will run it as a Zoom drop-in session for people that have to go through things individually. Okay, so if you do want me to cover things in class, that's fine. Just let me know. But if I get additional responses, then I will just run it as a Zoom drop-in session instead. Okay. Essentially, it's just an additional office hours. Okay, so today we are finishing the whole course and we're thinking about evolutionary epidemiology again, looking at some concepts about stability in an evolutionary sense, okay? So in the last lecture, well, actually, before we go talk about the last lecture, there's quite a lot of new terminology here. But most of this hopefully will make sense by the end of today. Okay. So in the last lecture, we were looking at the evolution of virulence, or the amount or extent to which a pathogen may damage its host. And we saw that if there is a trade-off between the extent of damage caused, which we were modeling through the mortality rate, and how transmissible that pathogen was, then this could lead to an intermediate level of virulence being optimal. Okay. And why might there be a relationship between these things? Well, this is basically saying that less transmissible pathogens, or rather less virulent pathogens are also less transmissible because they're infecting fewer host cells and host tissues. They're not producing as many new virions, say, if it's a virus or new bacteria, if it's a bacterial infection. And so pathogens essentially have to balance this relationship between their onwards transmission and the amount of damage that they're causing to the host. Okay, so the self-study problem at the end of last lecture looked at a particular example and got you to hopefully sketch what the selection gradient looked like. And from that, deduce that the pathogen would evolve to that singular strategy. So in fact, what I'll do is I'll just go back to that self-study problem. You should have had a selection gradient that looked something like this if you had sketched it, okay? So the point of this here is that a little bit like when we were doing our phase line diagrams before, this red curve is our selection gradient. When our selection gradient is positive, S of alpha is positive here. So this yellow region, selection is going to drive alpha to increase. So we're going to move to the right. And this green region here, S of alpha is negative. This red curve here is below the axis. And therefore, selection is going to push us to reduce alpha, reduce virulence. And then they meet here at this singular strategy. So the idea here is that if you were a little bit away from this, you're going to be moving back towards it on either side. And so you'll converge towards it. Yes.
How are you able to see the -1/2 there as like an asymptote?
That is because, let me just go back up for this sketch here. So this is just seeing, okay, what happens to S of alpha as alpha gets very, very large? So S of alpha we had as being this here. If we divide everything on the top and bottom by alpha, we'll get 1 plus gamma over alpha plus d over alpha. And we're going to be dividing by 2. If alpha gets very large, this and this will go to 0. We still have this -1 on the end, so we have a half minus 1, so we're 10 to minus a half. Okay, so the key thing is what's going on here. And we can see that if you move a little bit away from this singular strategy, you'll get pulled back towards it in either direction. So this is very much like our ecological stability that we looked at on phase line diagrams earlier in the course, okay? So this is all well and good here because we can do a nice simple sketch of this selection gradient, but we won't necessarily be able to do that in general. And therefore, what we want to do is think about how can we prove that a singular strategy is stable in an evolutionary sense, and what does it mean? There are different types of stabilities, it turns out, when we're talking about evolution. So that's what we're going to be doing today. Sorry. Also, just a quick advert, I will be running a 400 level special topics course on the mathematics of evolution that will run next summer. So if you are interested in learning more about this kind of thing, specifically the kinds of things we've been doing in the last few lectures, this course is a very good preparation for that course. There will be people taking this course who have not taken the current course, and therefore there'll be a certain amount of recap of the kinds of things we've looked at already. You know, we'll be thinking about evolution in the context of, say, predator-prey models or competition models, or as we've been doing here, infectious disease models, even thinking about what happens when both our pathogen and our host population are evolving or co-evolving together. So if you're interested in learning more about these things, these last 3 lectures are kind of a little bit of a taster as to more of the kinds of things we'll be doing in the summer, okay? But as I said, this course is a very good preparation for that course. Okay, let's move on. So I want to just start with a quick recap of the model that we looked at last time. So we're looking at a pathogen that followed SIS type dynamics. So there was no permanent recovered class here. There was density-dependent transmission at rate beta, a recovery rate gamma, and we had, for the first time, a disease-associated death rate alpha. And it's this alpha that we are allowing to evolve. We also had the host having a natural death rate D and a birth rate, which we set to be B is equal to D plus alpha times by I. And choosing this birth rate here meant that we could keep the population size constant. Okay, so you went through a few of these things last lecture, so I won't get you to do them again. But we found that the invasion fitness of a rare mutant, this W here is telling us a mutant pathogen with virulence alpha sub m that is trying to invade a population that already has a pathogen with virulence alpha. When it's rare, its invasion fitness, its per capita growth rate, is going to be equal to 1 over IM DIM dt. But IM is the density of individuals, or proportion in this model, I believe, of individuals that have this rare mutant. And we showed that was equal to beta of alpha m. So its transmission rate we're assuming is a function of its virulence. There's a correlation between these things. Divided by R naught of alpha. This was because we had our S star, so our endemic equilibrium proportion of susceptibles was just equal to 1 over R naught. So we call this R naught of alpha because that's determined by alpha, the current level of virulence. Then we had minus alpha m plus gamma plus D on the end. And then from this, our select gradient, S of alpha is just the partial derivative of our fitness with respect to our mutant trait, alpha m. And then evaluate this alpha m equal to alpha. So when we do that, we found that we had beta prime of alpha, so the first derivative of our transmissibility as a function of alpha, divided by R naught of alpha minus 1. And then finally, our singular strategy satisfies S of alpha star equal to 0. And from the equation above, this simply gives us beta prime of alpha star is equal to R naught of alpha star. So that was all the things that we had from the last lecture. So let's think about stability in an evolutionary sense, stability of this singular strategy. So really what we're saying when we find this singular strategy here is we're just finding a value or values of alpha star that satisfy this equation. We know that at this point here, the selection gradient is equal to 0, but it doesn't tell us anything about whether this is fitness maximum, whether it's a fitness minimum. It doesn't tell us whether we are able to approach that through small steps or not. So it only tells us that at that point, the selection gradient is not positive or negative. So we need to think about the stability of that, and we think about it in a couple of different ways. One is that we look at something called convergence stability. And this is tells us that if we are reasonably close to our singular strategy, we'll move towards it. And that's what we were showing on that selection gradient effectively that I sketched or showed the sketch of at the start, that if we move a little bit away from it, we'll move back towards it. So we're able to approach it through small steps. And then the other concept, so that concept is kind of very similar to the sort of attracting concepts that we've had before for stable equilibria in an ecological sense, right? If you move a little bit away from it, you move towards it. That's essentially what convergent stability is all about. But this time, rather than say population sizes, we're dealing with these trait values or phenotypes. Okay. The second is a little bit different. And this evolutionary stability is basically saying that no nearby mutants can invade. It turns out these things are different from each other. Okay, this one really is saying all about whether we have a fitness maximum or a fitness minimum. Okay. So like I said, in the self-study problem, you're asked to just sketch the selection gradient and therefore deduce convergent stability from that, but we're not always able to do that, in which case we need to look at our second derivatives or a selection of our second derivatives of our invasion fitness, and that tells us something about these two types of stability. So I'll deal with evolutionary stability first of all, because in some ways this is the easiest one to deal with. And the definition of this, we say that a singular strategy alpha star is evolutionarily stable if and only if the second partial derivative of our fitness with respect to our mutant trait evaluated with both alpha m and alpha equal to our singular strategy, if this is negative. And for ease, I'll just refer to this as a capital E, for evolutionary stable. So if this condition is satisfied at our singular strategy, then we have a fitness maximum. So what does this mean? I'll do a little sketch of this. Well, let's think about a slice through this function. So W is both a function of alpha m and our resident trait, or in this case here, our singular strategy. So it's a two-dimensional function, but we can think about taking a slice through this because we're just interested in the second one being an alpha star, which we're fixing, okay? So let's think about what happens if we vary alpha m. Well, we might have a scenario that looks something like this. If this is my invasion fitness, as I vary my mutant trait value, and if my singular strategy here, remember my singular strategy is telling me when my selection gradient is 0, in other words, there's a turning point in my fitness function. So alpha star could represent this point up here, this maximum here. And this corresponds to the case when E is negative. So what this is saying is that this value of virulence gives the highest level of fitness, so at this peak here, and any mutant nearby has a lower level of fitness, so it can't invade. So when this E is less than 0, E is defined up here. That's the scenario where we have a fitness maximum. If we compare that to the case when E is positive, so I'll do this over here, E is going to be positive over here. Again, we're going to sketch our fitness function passing through our singular strategy. And this time, maybe it looks something like this. Again, alpha star is telling us when we're having a turning point in our invasion fitness, because our selection gradient is equal to 0. So here, our selection gradient is equal to 0 again, but this time it represents a point where our level of virulence has the lowest level of fitness. Okay? So nearby mutants are all fitter than this one, and so they can invade. So just because your selection gradient is equal to 0 doesn't mean that you're going to evolve to that point. You could be in this scenario over here, where you're at a fitness minimum. Okay, so that's what evolutionary stability is all about, is determining whether you're at a fitness minimum or a fitness maximum. Convergent stability is all about whether you move towards that singular strategy or whether you move away from it. Okay, so just because, so this is all about whether you can, a mutant can invade or not. Here, this is about can you actually approach it through small steps. So if you remember the whole process, I've walked along this line here a few times to demonstrate this. What we're really doing here is we're saying there is a current level of virulence in this population. We let everything reach equilibrium, and then we say, okay, introduce a rare mutant, has a slightly different level of virulence, and then you see if this level of this phenotype can invade. And if it can invade, then we're saying it replaces this one, and then you keep repeating that process over and over and over again. So it's a process, this evolutionary process is essentially small mutations with invasion and replacement, and so on. We're not making a big jump in this space. I'm not jumping from one end of this line to another. We're making these tiny gradual steps. So what happens with convergent stability is it's telling us whether we're able to make those small steps with invasion and replacement of these different phenotypes, and we're able to approach our singular strategy these small steps. And if we're not convergent stable, that means that we've actually got a repeller in an evolutionary sense. So what that means is that we are repelled away, we're pushed away from that singular strategy, and we can't approach it through these small steps. So what's the actual mathematical definition of this? It's a little bit more complicated than before. We take our second derivative of our fitness function with respect to our mutant trait and evaluate this at our singular strategy. We need to add this to another second derivative. So this time we're taking a partial derivative with respect to our mutant trait and then with respect to our resident trait. In fact, in practice, it doesn't matter which order we do these things in. Again, evaluate it at our singular strategy. And the sum of these two things has to be less than 0. And the eagle-eyed among you may have noticed that the thing on the left-hand side was our E from above. So this evolutionary stability here also features in our convergent stability. But we have this additional condition here as well. And I refer to this condition here as M. So the sum of these two things, E plus M, just for shorthand notation, must be negative for us to move towards this singular strategy. Okay, so these two things, the convergent stability and evolutionary stability, are independent. So that means that we have 4 possible outcomes, depending on whether these inequalities are satisfied or not. So the first one, if our singular strategy is both evolutionarily stable and convergent stable, we have something that's called a continuously stable strategy, or CSS. What this is telling us that our singular strategy is both locally attracting, so we can move towards it with small mutations of invasion and replacement. And then once we get to that singular strategy, we're at a fitness maximum, we're uninvadable. So you move towards it, you can think of it as kind of like climbing a mountain. Once you get to the peak, nothing's better, and that's an evolutionary endpoint. Nothing can invade, and you've been able to approach that very nicely. So that's the scenario that we had essentially with our virulence evolution from the last lecture. We'll go into this in a bit more detail, showing it this upper method, using this upper method in a few moments. Okay, what about the second example here, where an evolutionary repeller is neither attracting, so you can't move towards it with small mutations, and it's also, it's neither attracting nor uninvadable. What do we mean here is that this singular strategy is a fitness minimum. Everything around it is fitter, so they can all invade, and you'll also move away from it. Okay, so this is kind of the opposite of climbing a mountain. It would be like a valley, and saying that everything around you is fitter, and you're climbing up away from that point. Okay, so you move away from that valley. The third one here, Garden of Eden, has a slightly strange name. It's essentially the same in many ways as a repeller, but it is evolutionarily stable. So this is a very strange scenario. What's going on here is we have a point, a singular strategy that is fitter than everything else nearby. It's uninvadable. So if you start there, you will stay there. However, it's not a point in this space that is attracting. So you can't approach it through small mutations. That means it's a point that is a fitness maximum, but we can never reach it. Think of it as being, again, like a mountaintop, but there's no path that will take you to the top of that mountain. If you start at the top of that mountain, if you could be helicoptered in, great, you're fitter than everything else, but you can't actually ever approach it if you try to do it through small mutations. This is a bit of a strange scenario, but functionally, it basically behaves like a repeller. Unless you happen to start at that exact perfect, point at the top of this mountain, either side of that, you just move away from it, and so it behaves basically like a repeller. You get pushed away. The final one, again, these last two are a little bit strange. The final one is where we have a point that is not evolutionarily stable, but it is convergence stable. We're not going to go into much detail about this today, but we'll be thinking about these different types of scenarios if you do the course in the summer. This branching point is kind of weird again, but it's saying that you take these small mutational steps, you move towards the singular strategy, but once you get there, it's a fitness minimum. And that means that everything around it can invade. So if I reach this point as a singular strategy, mutants on this side, as well as mutants on this side, would both be able to invade, and they can coexist. In fact, we need to look at a few more conditions to verify that. But essentially, the population now diversifies, in this case, into two different pathogens. They can coexist, and they have different levels of virulence. So if we imagine, if I draw a sketch of what this might look like over time, and suppose this was my alpha, my level of virulence, they would evolve to my singular strategy because it's convergence stable. It's alpha star. And then once I get there, nearby things can invade, and they can invade on both sides. So what happens now is we would get a branching point here. And so in the context of our model, this would correspond to a relatively low level of virulence in one strain and a relatively high level of virulence in another. This last type of outcome, this evolutionary branching point, tends out to be really important in terms of understanding patterns of biodiversity, because it tells us how we can generate diversity within populations by evolving to these singular strategies and then having something called disruptive selection, which pushes you into these contrasting phenotypes. Okay. In terms of something like in an exam, I might ask you to classify, given your derivatives, maybe calculate derivatives and then classify what they are. I wouldn't be asking you to do, say, a sketch of what that looks like. Maybe I would. I'm going to take that back. Maybe I might ask you to do a sketch. You see, I haven't written the exam yet. What I would not expect you to be doing is to be going into lots of detailed explanation, because this is the last thing in the course. I really just kind of wanted to introduce these concepts to you. Okay, so it would very much be a small component, like classifying. You might be asked to classify something, but then going much beyond that, I wouldn't really expect too much. Okay. Kind of disregard a lot of what I just said. I thought of a good question I could maybe ask you guys. Okay. What we're going to do now is we're just going to do a little bit of practice of this and apply these ideas to understand evolutionary stability and convergent stability to our virulence evolution model that we looked at before. And so let's work through the evolutionary stability first. Shall we work? I'll tell you what, we'll take a vote. Who would prefer me to work through this? Hands up. 1, 2, 3, 4. Okay, you've already got a majority. That's fine. Okay. So we'll start off with our invasion fitness. Okay, so W, this was beta of alpha M over R naught of alpha minus alpha M plus gamma plus D. Now, our evolutionary stability was our second derivative with respect to the mutant trait alpha M evaluated at our singular strategy. Now, I'm going to leave everything in its very general sense here. I've not defined what this function beta of alpha is. But if we take our first derivative with respect to alpha M, that's actually just before, it's very close to our selection gradient. It's just we haven't evaluated it at alpha at that point. What are we going to have? If we take the first derivative of this with respect to alpha M, we're going to have beta prime of alpha M over R naught of alpha. And then this bracket here is just going to go to -1. It's linear in alpha M. And then we take our second derivative with respect to alpha M. So we'll have beta prime twice. So the second derivative of beta of alpha M. R naught of alpha is just a constant, it's a coefficient, so it just stays the same. And we had a -1 here before, and so that drops down to 0. So we're going to get beta prime of alpha, in fact, alpha star. So we're evaluating this at our singular strategy. So the second derivative of our trade-off at our singular strategy divided by R naught at our singular strategy has to be negative. And this R naught here is always positive, right? It can't be negative. So this happens if and only if our beta double prime alpha star is negative. So we haven't used a function here, but we can do a little sketch and think what this looks like. Suppose we've got our alpha going along the horizontal axis and our beta is a function of alpha on the vertical axis. Suppose we've got a relationship that looks something like this. Suppose we've got another function. Actually, I'll do that one afterwards. Let's keep it to just one for now. Suppose my singular strategy is here. In this scenario, in this purple curve, beta double prime of alpha star is negative. This curve is sloping this way. It's negative, and so with this type of relationship, if it's curving down like this, then regardless of what that trade-off actually is, you know, whether it's going there or whether it's going here or whatever, as long as this alpha star has curvature that looks like this, then it's going to be evolutionarily stable. If you contrast that with this green curve here, beta double prime is positive, and so in this scenario here, it's not going to be evolutionarily stable. Why do we care then? What does this all tell us? Well, ultimately, remember what we're talking about here is two biological traits: virulence and mortality rate and transmission. And we're saying that we'll evolve, or rather our singular strategy is uninvadable. It's an optimal strategy. We don't yet know if we're going to move towards it or not. It's an optimal strategy if our relationship looks something like this, but not like this. So what's this purple curve saying? It's saying that virulence is eventually increasing much faster than transmission. Okay, we're kind of curving this way here. Doesn't mean that we're necessarily plateauing, but it's increasing like this. So eventually, we're increasing our virulence much, much faster than we're increasing our transmission in the purple case. So that's telling us that the costs of increasing our transmission rate are becoming greater and greater. In other words, they're becoming increasingly costly. This is an example of diminishing returns. So down here, a little bit of an increase in virulence leads to a big increase in transmission. But over here, a big increase in virulence only leads to a small increase in transmission. And so it's not worth paying the costs of being more deadly if you're not getting much back in terms of transmission. Whereas if we flip it around and think about this green curve here, over here, a relatively small increase in virulence leads to a very big increase in transmission. And so here you tend to get selection pushing you to higher and higher levels of virulence because we have increasing returns as opposed to diminishing returns. Okay. This here is just an example using our trade-off from the self-study problem from last lecture. What happens if we choose a specific trade-off now? Well, we want to verify that alpha star is evolutionarily stable when this trade-off is given by a square root of alpha. So we take our second derivative. This is going to be minus 1 over 4 alpha power of 3 over 2. That's just a bit of calculus. Taking our second derivative of this function gives us this. And because of this minus sign in front, and alpha is always positive, this is always negative. So it doesn't matter where exactly my alpha star is in this scenario, regardless of where it is on this purple curve, for example, it is always going to be a stable singular strategy. Really, what we should be doing is we should be evaluating this at alpha star. So, for example, if you had a curve that looks more like, I'll just sketch it on here. If you had a curve that looked more like this, the curvature is changing from curving up to curving down. And so you don't just know that, that wherever alpha star is here, for example, it would be evolutionarily unstable, but if alpha star was here, it would be evolutionarily stable, right? So you should really look at it at the singular strategy. Here, because there's no change in direction, there's no change in this curvature going from, say, concave down to concave up, or vice versa, we know that for any value of alpha star, this would always be satisfied. So here, what have we shown? We've shown alpha star must always be evolutionarily stable. In other words, it's a fitness maximum. It's a fitness maximum and it's uninvadable. Okay, so that tells us that we're a fitness maximum, we're uninvadable, but it doesn't tell us whether we can approach it. Think of it as like this example of a mountain, where the top of the mountain represents your fitness maximum. Alpha star sits at the top of a mountain rather than in a valley. Question is there a path that takes us to the top of that mountain or not? So it's a little bit more tricky to calculate this in general. And so we're going to stick with this same example here, where we have beta is equal to the square root of alpha. We want to ask, when is alpha star convergence stable? Okay, so let's write our invasion fitness with this function here. So we're going to have square root of alpha m. So we're just substituting in beta of alpha here, beta of alpha m in this case. Our R naught of alpha is going to be alpha plus gamma plus d, or rather 1 over R naught of alpha is equal to alpha plus gamma plus d divided by square root of alpha now. So the bit that I'm about to highlight in green, this is just my R naught of, or rather 1 over R naught of alpha. And the bit in yellow is just my beta of alpha m. And then we're going to subtract alpha m plus gamma plus d. So nothing's just there. Okay, I'm going to do this in stages, just so it's clear what I'm doing. I'm going to first take my derivative with respect to alpha m. If I do that, I'm going to get alpha plus gamma plus d over 2 root alpha m times by root alpha. So the bit in green is just a constant when we're taking a partial with respect to alpha m. So we're just taking the square root of alpha m, take the derivative of that, and then multiply it by the bit in green. So we get 1 over 2 root alpha m, and then multiplied by the bit in green. And then we're going to have minus 1 because the second term is linear in alpha m. Just for ease, I'm going to take this 2 root alpha m out front. We have alpha plus gamma plus d over root alpha, and then the minus 1 on the end. Now let's think about taking the derivative of this with respect to alpha. It's a little bit more complicated now. We're going to have to use the quotient rule. So we still have this 1 over 2 root alpha m at the front. Shouldn't be a root 2, should just be a 2. And if we use the quotient rule on the bit that I'll circle in red, put in a bracket, we're going to have, hopefully I won't make a mistake here, root alpha. So take the derivative of the denominator, multiply it by, sorry, take the denominator, root alpha, multiply it by the derivative of the numerator with respect to alpha. So that's going to be linear in alpha, so that's just going to be times by 1. And then subtract our numerator, alpha plus gamma plus d, times by the derivative of our denominator. So 1 over 2 root alpha now. And then divide by our denominator, root alpha squared. And then we still have this minus 1 at the end. In fact, we don't have that minus 1 at the end because we've taken our derivative and we lose that minus 1. So the constant drops out. Okay, let's now evaluate this at alpha m and at alpha m equaling alpha. Yeah, alpha m equaling alpha. So exactly what we had on the line before, but now we're just going to say alpha m is equal to alpha. So I'm going to split out into 2 fractions. So given by the green and the pink bits. So the pink bit, we're going to have root alpha over 2 root alpha. So those are going to cancel. And then we'll have a 1 over root alpha squared. So that's going to be just 1 over alpha. And then we've still got a factor of 2. So we're going to have 1 over 2 alpha from that pink term. And then we're going to be subtracting, let's see, we'll have still our alpha plus gamma plus d on the numerator. And we will have our factor of 2. We're also going to have this thing here that I'll circle in red. That 1 over 2 root alpha is going to, the 2 root alpha is obviously going to come onto the denominator here. So we'll have 2 root alpha times by 2 root alpha. So that gives me a 4 alpha. And then we've got this root alpha squared as well. So that just gives me an alpha. So we'll have 4 alpha squared on the denominator. This is a little bit messy. It's just a bit of calculus. We can combine those just into one fraction, and we'll get alpha minus gamma minus d over 4 alpha squared. Hopefully I've not made a mistake. Please let me know if I have. Okay, the final step is that we want to evaluate this. Our m is going to be the previous line evaluated at our singularity. Now, our singular strategy was shown in the self-study problem to be equal to gamma plus D. This is from self-study. In the last lecture. So what we need to do now is substitute this singular strategy into what we had from the previous line above. So we have alpha is going to be replaced with gamma minus D, sorry, gamma plus D. So we can have gamma plus D. That's our alpha star. We still have a minus gamma and a minus D. And then we're going to be dividing by 4 gamma plus D all squared. And you should see that this gamma and this D are going to cancel with each other. And so this is equal to 0. That's quite nice because remember that our convergence stability is given by E plus M. And we've already shown that E, which was our evolutionary stability condition, we've already shown that this was negative. So because this second condition, the second component, second term is equal to 0, our convergence stability is implied here by our evolutionary stability. So it's convergence stable when it is evolutionary stable. This is not true in general. This is just for this particular type of trade-off in this particular model. But we happen to have found that evolutionary stability implies convergence stability here. So let's sum that up. What happens to virulence evolution in this model? For this particular type of trade-off, we therefore have that our singular strategy is evolutionary and convergence stable. And so alpha star is what? May you remember from the definitions or scroll back in your notes? CSS, a continuously stable strategy. In other words, in that analogy of a mountain, it is a fitness peak and there is a path that leads us to that peak. So we'll take these small mutational steps. Again, think about the context here. What's going on is got a pathogen in a population that has a certain level of virulence. Small mutations will change that level of virulence until we reach this optimal level of virulence here, alpha star. Once we get there, we stay there. Nothing can invade, nothing is better than that. So virulence evolves to alpha star and stays there. This alpha star is what we call gamma plus D. This is kind of a, you can almost think of these two parts being a bit of a mathematical explanation as to, a mathematical description, and here is something that's slightly more of a biological description. What does this tell us? Well, it tells us some interesting things. It tells us that the level of virulence is equal to the recovery rate and the natural mortality rate of the host. So that means that if the recovery rate increases, so say you start introducing some new treatments that increase the rate of recovery from this infection, this is going to select for pathogens that are more deadly. So doing these types of models can give us these sorts of qualitative predictions where we can say, okay, if we do some sort of change, if we have some sort of public health intervention, what are the downstream evolutionary effects that we might expect? So in this case, if we have new treatments that increase recovery, we might select for pathogens that have a higher mortality rate, essentially to compensate for this. Yeah. Okay, nearly there now. The last thing I wanted to introduce is something called a pairwise invasion plot, or PIP. Now, these pairwise invasion plots are essentially just a graphical representation of this whole process that we're doing. And they usually look something like this. what these are doing then, they're saying on our horizontal axis, we have our resident trait. So in our model, this is just alpha, and it's increasing in this direction. And on the vertical axis, we have our mutant trait, alpha m. That's increasing here. And then along this main diagonal, from bottom left to top right, we've got alpha m equal to alpha. And if you recall, what we're doing in this process is we're thinking about what happens if we have a small mutation. So we're kind of understanding what happens as we move along this main diagonal when alpha m is approximately equal to alpha. Now these regions here, the shading, the shaded regions with the plus in them indicates that the mutant can invade. It has positive invasion fitness. And the white regions with the minus tell us that the mutant has negative invasion fitness, and so it can't invade. So let's think about what happens. Suppose we are here. This is our current level of virulence. Let's call it alpha naught. We're going to have a small mutation. And suppose this small mutation slightly increases virulence. So this is my alpha m. I'll call it alpha m. So there's a slightly different level of virulence. Because we're in this region here now, we can invade. And so it replaces our resident and becomes our new resident. So this is now my alpha, let's call it alpha 1 there. And then we repeat that process. Remember, we're just doing this process of mutation and invasion and replacement and so on. If I keep doing this, these mutants with higher virulence can invade until I get to this point here. When I get to this point here, it's not super clear on this diagram, but because this white region above and below this point here at this intersection, we have a white region above and below, which means that mutants that have higher levels of virulence or lower levels of virulence can't invade. And so we have a fitness maximum. So that the fact that we've got a white region above and below tells us we've got a fitness maximum. So that tells me that it's evolutionarily stable. If it had these shaded regions above and below, that vertical, then it would be evolutionarily unstable. We could invade. And then this sort of staircasing here is telling us, can we approach it using small mutations? So this is telling us, are we able to converge to it? So it's telling us about our convergence stability. So in this particular scenario here, these pairwise invasion plots are another way of working out a singular strategy here. This is my alpha star here. This singular strategy here, is it evolutionary stable? Is it convergent stable? We can represent it using these pairwise invasion plots. Convergent stability is all about, can we move towards this point or are we driven away from it? And if we have the white region above and below that point, then it's uninvadable and therefore it's evolutionarily stable. So these are just a way of visualizing this whole process that we've been talking about the last few lectures. The self-study problem I'm going to leave you guys with is thinking about what happens when we change the orientation around and think about different types of pairwise invasion plots. Thinking about how these relate to the different types of outcomes we have. So have a go at those in your own time and thinking about this. What happens if you start at a point, you invade in the shaded regions, and then that becomes your new thing, your new resident, and then you repeat that process. Do you move towards the intersection in the middle, or do you move away from it? And if you are at that point, can anything nearby invade or not? So can we invade above or below? I will leave that for you guys as a self-study problem. And that is it for today. I'll stick around for a minute if you have any questions. If not, a reminder, Friday is a quiz. We will be doing some things related to evolutionary epidemiology. So it gives you a bit of a hint as to things to look at. Obviously, it's open book as well, so you will have your notes available. And a reminder, please don't submit your projects late because there are penalties for late submissions. Okay? Yes, you have a question. Yeah.
So when we interpret mean like here like the region with like the plus and the minus, like when like there like you're like above the line, so you move right. This is positive.
Yes. So what we're doing here is we're saying, okay, this is your, imagine this is your, when you're on this line, there's only one type in the population, one phenotype, one level of virulence. So that's our system settling down to its long-term endemic ecological equilibrium. And then we're introducing that rare mutant. So when we introduce that rare mutant, we're saying, okay, this is our rare mutant here. Because we've introduced a rare mutant that can invade, it's in this positive region, it invades and replaces our current resident. And so our new resident is just the same level of virulence here. So we go back to the diagonal. If we'd tried to introduce a rare mutant that had lower fitness here, it wouldn't have been able to invade, and so we would just go straight back up to the diagonal. So basically, you move back to the diagonal if it can invade, go horizontally if it can't invade, you go vertically. But kind of always just, it's kind of pointless thinking about what happens if you go into this region, other than you just go straight back to the line. It's more about what happens if you go to the positive region, where do you go from there? And I'm only going right because that's where the diagonal is. If it was the other orientation, then I would go left. So for example, if I start up here and I have a very high level of virulence, in fact, I'll sketch it on, it'll be easier. If my initial level of virulence was up here and my mutant was above, it's less fit, so it can't invade. So I just go straight back to the main diagonal. If level of virulence of my mutant is lower, and this is my alpha M now, alpha M, call it 2, alpha M2, it has positive fitness, so it can invade. I again move horizontally to the diagonal, so this time I've moved left. And here you'll see, if I keep repeating this process of introducing a rare mutant, I'll approach it from the other side. Any other questions? No? Okay. Well done for reaching the end of the course, as a new material. Reminder for those who weren't here at the start, I have sent out a survey asking if you want me to cover anything in particular for Monday's review lecture. I have only received one response so far. If I don't receive more responses asking me to cover more things, I will just run it as a Zoom drop-in session, like an extra office hours, because there's not really much point if people don't want me to cover stuff in particular. So please let me know if there's things you want me to cover. If not, I will run it as a Zoom office hours. Okay.